Hello, hello. This is Dr. Jenkins, and here I am recording for you a video on blood vessels. So this chapter can be sneaky hard. We started this chapter by talking about the structure of arteries, veins, and capillaries. So you'll remember that all arteries and veins have the same three layers in their wall: tunica externa, interna, and media. But there are slight differences. Arteries have more smooth muscle. Arteries are elastic. Veins have less smooth muscle, are larger in diameter, and not elastic. They tend to collapse, and veins contain valves. Capillaries form a capillary bed and are very thin-walled. So that's kind of the more straightforward part. Now we're going to get into some ways in which the blood works. I introduced this in lab a little bit, and lecture, I think. We need to be able to shift blood to the right part of the body at the right time. Yes, there's always some blood going everywhere, of course, but we need to shift more blood to some areas at certain times and less blood to other areas at other times, but all while maintaining blood pressure. So there's actually a lot going on. So I picked up where we left off. We finished talking about the structure of arteries, veins, and capillaries. So make sure you get that easier stuff. And one more piece of business before we start to really talk about the fluid dynamics. Check this out. At rest. We're talking about at rest. I'd like you to know that at a given point in time at rest, look at where most of our blood volume is. Most of our fluid volume tends to be in veins. And that is because the pressure that blood goes through in veins is much lower. So if we were to compare arteries and veins, blood moves through arteries in quick whooshes. This makes sense because when the heart contracts, blood comes rapidly moving through an artery. And then there's a period of time where we really don't have much blood moving through an artery. So because arteries are connected to the heart, the big pump, blood moves through arteries quickly and then rest. Quickly and then rest. Versus veins. Veins don't have the benefit of being closer to the heart. So there's a much lower pressure gradient. Plus, venous blood is moving against gravity. So it's harder to move blood through veins. As such, it moves slow, 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 instead of a big whoosh followed by almost no blood. So because of that, at a given point in time, because it's harder to move blood through veins, there's more blood collecting in veins at a given time. You don't need to know this exact breakdown, but have an idea that the majority of blood at rest is in veins. How much? Well, about 2/3. All right, so here we go. This is kind of the harder stuff, but don't worry. Just like we have for other things, we're going to introduce it in pieces. I encourage you to memorize these things in pieces. So what did we start with? We started with structure of arteries, veins, nerves. Arteries, veins, capillaries, excuse me. Start with structure, easy. Then remember, at rest, where do we have most of our blood flow? Veins, about 64%. Now we're going to introduce some other concepts. Here we go. From here on, when I talk about blood flow, what I'm really talking about is the amount of blood delivered. Kind of what you would think. More blood flow to an area means there's more blood being delivered there. That makes sense. The word that might be new to you is perfusion. Perfusion really is a measure of rate, and it's rate of tissue infusion. What that means is exchange at capillaries. Exchange at capillaries. Remember, the heart pumps out blood through arteries. The arteries take that blood to a tissue, let's say a muscle, And once we bring blood to the muscle, what do we have to do? We've got to exchange. What are we going to drop off to the muscle? Oxygen, glucose. What are we going to have to pick up from the muscle that's a waste product? Carbon dioxide. And those waste products will then return back to the heart from the veins. So when we talk about perfusion, it's the rate of exchange at capillaries. Usually it goes hand in hand. Usually when there's more amount delivered to an area, there's more exchange of things at the capillaries. Not always, but we have to do this first. So we first have to get the blood to a tissue. So flow always comes first. And then we perfuse or exchange into the tissues what is needed. But you can keep it simple and you can just say blood flow is the amount of blood. And then when we think of perfusion, it would be rate of exchange at the capillaries. All right. I give you some examples, but you don't need to know this. So for now, don't worry about that. Here's what I want to get to. And for some reason, when I upload this PowerPoint into this program, GoodNotes, the arrows sometimes don't come through. So we're going to be talking about some fluid dynamics, and related to that is an equation, but don't worry. What this is saying, flow, this should be, is proportional to, is proportionate to, that's what that symbol is supposed to be. Flow is proportionate to change in pressure over resistance. So this first one is supposed to be the proportionate to. The second one is supposed to be delta, which is change. Okay. Excuse me. Grab a tissue here. Flow is proportionate to change in pressure over resistance. It's another way of saying equal. It's just a little bit less certain, but for our purposes, it's like equal. So look at the numerator. Flow is on the left-hand side. What's on the numerator over here? Change in pressure. So that means that change in pressure and flow are directly related. When there's a high pressure gradient, there's a high flow. So whatever is happening here is happening here because change in pressure is on the numerator. When there's a high pressure gradient, there's more flow, more blood flow. Think of water moving down a river. When there's a bigger pressure gradient, when it's a steeper hill, doesn't blood or water move faster? When the heart pumps harder, when there's more force, there's a bigger pressure gradient between the heart and the vessels it's pumping into. So the bigger the pressure gradient, the more flow. However, resistance is on the denominator. So that means that resistance and flow have an inverse relationship. When we add resistance to a vessel, it will decrease flow. When we add resistance, it will decrease flow. Excuse me. We're going to talk about more examples. So right now, I just want you to understand this equation, knowing that we're going to talk about it much more. Flow is proportionate to change in pressure over resistance. Change in pressure is going to have the same relationship with flow. When there's a high pressure gradient, more flow. When there's a low pressure gradient, less flow. However, resistance, because it's on the denominator, has an inverse relationship with flow. When we add resistance, it will decrease flow. Again, I apologize. So we're going to talk more about this later, but really important. Don't worry about this. Okay. Let's take a moment to quickly define blood pressure. Blood pressure is, you know what blood pressure is. You go to the doctor, they take it, either manually or with a machine. It refers to the force that blood exerts against a vessel wall. Usually, we're talking about systemic arterial blood pressure. So we're usually thinking about arteries. For this class, we don't need to worry about mean arterial pressure, MAP. We just need to know what the traditional blood pressure is, and we're referring to arteries. The force that blood exerts against that artery wall, force. The normal blood pressure is 110 or 120 over 80. The unit is millimeters of mercury. That's the same unit for barometric pressure out in the atmosphere. Check it out, folks. The top number is the pressure in the arteries during systole, ventricular systole. The bottom number is the pressure in the arteries during ventricular diastole. Amazing. Wouldn't there be a greater pressure during ventricular systole? Because that's when blood has been pumped out. So when we recently pumped blood out, there's more blood, therefore more force against the arteries. There's less pressure during diastole. There's still going to be some blood in the arteries, but less blood and not as much force because the heart has just relaxed. You can treat these as simple things to remember. So again, I'm encouraging you to study it in pieces. This whole chapter we started with the structure of arteries, arteries, veins, capillaries. Then we talked about resting blood distribution, that at rest about 64% of our blood is in veins. Then we introduced definitions of flow and perfusion. Flow is the amount of blood. Perfusion refers to the rate of tissue exchange at the capillaries. Then we introduced some equations. Flow is proportionate to change in pressure over resistance. Go through that. Now we're just defining blood pressure. The force that blood exerts against arteries. The normal blood pressure in arteries, usually taken at the brachial artery, is 120 over 80. 120 is the pressure during ventricular systole. 80 is the pressure during ventricular diastole. Boom, boom, boom. Look at what happens with blood pressure as we go further away from the heart. I guess I can use red here. When we talk about blood right as it comes out of the heart into the aorta, high pressure. But look at the significant drop. Once we get to the veins, because we're so much farther away from the heart, the pressure is much lower. I am not going to ask you these numbers other than 120 over 80, but I just wanted to show you how significantly the pressure drops. We're getting further and further away from the heart, and more blood is being distributed to tissues, so of course the pressure is going to drop. You should know the basic definitions. Hypertension is high resting blood pressure. Hypotension is low resting blood pressure. The key thing is resting. When we exercise, what do we expect to happen? When you exercise, your blood pressure goes up. But that's because we're exercising and we need it to. We're talking about at rest. That number, 120 over 80, is a normal resting blood pressure. When we're exercising, we do expect it to go up, but at rest, we don't want it to. Just know the definitions. Hypertension is when your blood pressure is too high at rest. Hyper means more. Hypotension is when your blood pressure is too low at rest. You can handle that. All right. Now we're about to introduce another set of equations, another equation. We're going to summarize this, don't worry, but please study it in pieces. We're going to put it all together later, but can we study it in pieces now? When you study it in pieces, you'll just memorize it, it'll get in your head, and then you got it. So another important equation for us is blood pressure is equal to cardiac output. We also learned that as Q. Here we're going to call it cardiac output, but it is Q. Blood pressure is equal to cardiac output times peripheral resistance. Just think about resistance. We also talked about, what was the first one? flow is proportionate to change in pressure, pressure gradient, over resistance. So here we have two equations. Let's first memorize and talk about them separately. We already talked about flow. This is blood flow, the amount of blood moving through. Up top here, we're talking about pressure. So looking at two different things. The one on the bottom that we've already talked about is flow. We know that when there's a high pressure gradient, I got that backwards, but when there's a high pressure gradient, there's more blood flow. When we add resistance, what does that do to blood flow, though? It decreases flow because resistance is on the denominator, so it has an inverse relationship with flow. Well, now, separately, even though they're related, separately, let's just first address this other one. Blood pressure is equal to cardiac output times peripheral resistance. Because they're all on the same, there's no denominator, it means that everything here has the same relationship. If cardiac output goes up, what happens to blood pressure? It goes up. Everything across this equation is linear. It's related the same way. That should make sense. If I increase cardiac output, I pump out more blood. If my heart pumps out more blood, if there's more blood in the arteries, won't there be more pressure? Because pressure is a measure of the amount of force blood exerts against the vessel wall. If I pump out more blood, there's more force. Here, though, we can also look at resistance. If I add resistance, that also increases blood pressure. So, here's my suggestion. Memorize these separately first. Then we're going to put them together. So I'm going to go back to the flow in a moment. Let's just spend a little bit more time talking about pressure. Pressure. So blood pressure is equal to cardiac output times peripheral resistance. What I would do is, when you get your next exam, I would write this on the side. Do you ever do that? Get an exam before you even start. Okay, right. I remember blood flow. I would actually write it in the corner. Blood flow is proportionate to change in pressure over resistance. Okay. Then I remembered that blood pressure is equal to cardiac output, or Q, times peripheral resistance. I would just get that on paper. And then when I ask you a question about it, you can go back to the little key you made, right? If I ask you, if we increase peripheral resistance, what is its effect on blood pressure? I could go back to my equation. Oh, right, if I increase resistance, this is all in the same line, so if resistance goes up, so does blood pressure. So for pressure, the things on the right are directly related to blood pressure. If cardiac output goes down, blood pressure goes down. So whatever happens to things on the right, it's the same thing to blood pressure. If I lower resistance, pressure goes down. Okay? Let's talk a little bit more about this pressure. If I skip something, don't worry about for now. Let's talk for a moment about resistance. Here, we tend to talk about peripheral resistance. We're just talking about resistance in the arteries and veins. You don't really have to even include peripheral. We're just talking about resistance in the arteries and veins. Resistance in arteries and veins. There's a lot of things that can influence resistance. If the blood becomes thicker, if we increase the thickness, it becomes more viscous, that's more resistance. If a blood is thicker, it's more resistance that the blood faces because it's thicker. And if I increase resistance, what does it do to blood pressure? It goes up. So one thing that could influence that is thickness. If the blood becomes thicker, more resistance. Another thing is vessel length. There's always going to be more friction the further away you are from the heart. So the further away, once I get to my radial artery, there's more resistance than there was right in the aorta, simply because we've increased the length of the vessel. I'm not as concerned about vessel length. That's true, but I'm not so concerned about that. I just want you to know viscosity. If the blood becomes more viscous, it's thicker, that adds resistance. And radius. Vessel radius is the #1 thing that affects resistance. Because it's not that common that our blood viscosity changes, really. It's possible, but our body's pretty good at maintaining a normal viscosity. So while it could happen, a change in blood viscosity, it's not very common. But what we do have commonly is changes in vessel radius. Okay, so here's what I want to talk about. This is the most common way that we influence resistance. Most common way resistance is altered in blood vessels. Like I said, viscosity can change, but it's not as common. But the most common way that we alter resistance is by changing the vessel radius. And what's the most common way that we change the vessel radius? Vasodilation and vasoconstriction. Sometimes on purpose, sometimes not on purpose. So, the biggest influence to our blood resistance is vessel radius. And we affect vessel radius by vasodilation and vasoconstriction. When we vasoconstrict, the vessel is narrowed. That increases resistance. If the vessel is smaller in size, there's not as much space for blood to move through, so there's more resistance. When I increase the resistance, I increase the pressure. Ignore flow for now. So when we vasoconstrict, vasoconstriction increases resistance, which increases pressure. When I vasodilate, now the vessel's bigger. There's more space for the blood to go through. So if there's more space for the blood to go through, I'm lowering resistance, which lowers the pressure. Because remember, resistance and pressure have a linear relationship. So in vasoconstriction, when I narrow the vessel, less space for blood to go through, there's more resistance. Anytime there's more resistance, there's more pressure. Vasoconstriction. In vasodilation, the vessel's wider in diameter. There's more space for blood to get through. So in vasodilation, there's less resistance. When there's less resistance, there's less pressure. All right. So let me just go back for a moment and let's just do a little review. So, start a new one here. Here we go. That didn't work out so well. New, notebook, create. So let's just, I don't mean to beat a dead horse, as my mom used to say, but, you know, maybe make a list of the topics that are important for this chapter, like right in front of your notes. So far, we've talked about structure of arteries, veins, capillaries. That will be your first order of business to study. Once you've memorized that, you can cross it off. Then we talked about resting blood distribution. Do you remember? At rest, about 64% of blood is in veins. Once you've memorized that, great, move on. I'm forgetting what we talked about here. Then we talked about definitions. We defined flow and perfusion, right? Flow, the amount of blood going to an area. Perfusion, the rate of tissue exchange at the capillary. Once you've memorized that, great. Let me go back from it, just to make sure I'm not forgetting. Oh yeah, we talked about blood pressure, right? Principles of blood flow. Yeah. Then we did, let's just go out of order here though. Let's just do definition, normal value of blood pressure. So we said blood pressure is the amount of pressure that blood exerts against a vessel wall. Normal blood pressure is 120/80. And then be able to define hyper and hypotension. Hypertension is abnormally high blood pressure at rest. Hypo is abnormally low blood pressure at rest. So give yourself a framework. If I make a list like this, then I go back to my notes and it's not as scary. Once you got that, then we talk about the equations. So our first equation, there was a piece of hair on the screen there. Our first equation was blood flow is proportionate to change in pressure over resistance. And then know the relationships. Change in pressure and flow are directly related. When there's a high change in pressure, high flow. Because resistance is on the denominator, that has an inverse relationship with flow. If I add resistance, if I increase resistance, flow goes down. Then we talked about blood pressure is equal to cardiac output times peripheral resistance. Because it's all in one line, anything on the right that changes, it's the same change to blood pressure. If cardiac output goes up, pressure goes up. If resistance goes up, pressure goes up. Then we talked a little bit more about pressure and resistance. What are the ways in which we can alter resistance? We can alter resistance by changing viscosity of blood. When the blood is thicker, it adds resistance. But the biggest way that we change pressure is radius of vessel. And that would be our vasoconstriction, vasodilation. When an arterial vasoconstricts, because it's going to be an arterial, remember? They're the only arteries that can really do this. If an arterial constricts, smaller space for blood to move through increases resistance, which increases pressure. When we vasodilate, there's more room for blood to go through. Resistance goes down, pressure goes down. Okay. After you've done this in order like this, like come back the next day, right? Sometimes people try and learn too much at once. Memorize this, try and memorize this for an hour. Then go do something else, come back to it again, review. Go do something else, come back to it the next day. This is what it's going to take. If you just try and memorize it all at once, it's just too much. Once you've got this down, then we need to put these two together. And that's where, on some of these slides, you'll see I've got a picture of a garden hose. So let's put those together. You're not going to be able to do this until you memorize everything else. So don't study what I'm about to say until you can say that you've gone through all of these. But now let's put it together. So you're going to be able to just write these at the top like it's no big deal. You're going to be able to write blood flow is proportionate to change in pressure over resistance. Then you're also going to be able to say blood pressure is equal to cardiac output times peripheral resistance. You're going to know it, you're going to understand it. The garden hose example is helpful when it comes to resistance. So resistance is, I think, the piece that can be challenging. If I know my equations, well, then I can figure it out. If we add resistance, so if I increase resistance in a vessel, if I add resistance, what is its effect on flow? Remember, resistance, if I add it here, it's inversely related to flow. So if I add resistance, it will decrease blood flow. But on the right equation, if I add resistance, because everything's related here, it's going to add pressure. So resistance can be a little bit tough. You're going to know this because you're going to memorize the equations. But I just want to put it together for you. The example that I give for this is the garden hose. So check it out. A garden hose. If you turn on the spigot and you allow water to come through the garden hose, the amount of water coming out would be the flow. If I was a better drawer, I would draw this, but I really can't draw for crap, so you're just going to have to listen. So if I turn the spigot or faucet greater, if I want more water to come out, that's an increase in the pressure gradient, increase the flow. If I turn on the spigot more, there's more force coming from the pump. If I increase the pressure gradient, more blood comes out. That makes sense. Let's talk about resistance. When you keep the end of the hose open, it's wide. There's low resistance, low pressure. But what happens if I add resistance? So the way to add resistance to a garden hose, is what you do with your friends during the summertime. You put your thumb over the edge of the end of the hose so you can squirt someone, right? So this is an example of what we're trying to talk about. If I turn the spigot on, I got the garden hose working, but then I purposely put my thumb over the output thing, and it sprays the water. So when you put your thumb over the edge of it, there's less blood flow. There's less water coming out. When I put my thumb over the edge of the garden hose, less water comes out because I've made the space smaller. I put my thumb over some of the output. Less water comes out. But the water that does come out is at a higher pressure. That's why you want to spray someone. So less water is coming out, but there's more pressure. It's the same thing in vessels. When we vasoconstrict, not as much blood goes through, but the blood that does go through comes through at higher pressure. You need to know this. This would be the example during vasoconstriction. If I constrict an arteriole, not as much blood goes through, but the blood that does go through goes through at a higher pressure. All right. Good, good, good. So now you've put those together. Let me look at the time here. So I think what I want to do is I want to start this next discussion, but then we're going to pick it up in person. I want to outline this, and then we're really going to get into it when we meet in person. Now we're going to talk about regulation. How do we regulate blood pressure and blood flow? This is the essence of how our body is able to do what it needs to do. This is what I've been saying all along. Our ability to purposely direct more blood flow in one area to less blood flow in the other. It also relates to pressure. Sometimes I need more pressure over here in this part of the body, but less pressure over there. So it is critical that we have the ability to do this and maintain homeostasis and then send things where they're needed. We're going to outline this regulation in 3 ways. The first 2 ways, and I have this written kind of funny. Let's just do it this way. There's 3 ways that we can regulate blood pressure and blood flow. The first 2 are short term. The first 2 regulators are short term. The third one is long term. So we have a way to regulate blood pressure and flow in the short term, which kind of carries us over, but ultimately we're always going to be relying on hormonal control for long-term regulation too. The way that we do this, number one and two, we regulate blood pressure and flow by altering resistance, largely. When we get to the hormonal, we're going to be able to affect flow and pressure through blood volume. It's all going to make sense. Let me just introduce this and then we'll be done. We're talking about how we regulate blood pressure and flow, how we get the right amount of blood to the right part of the body when it's needed. We can do it locally and through neural. Those 2 are short term. And then we can use hormones long term. I just want to talk briefly about number 1 because it's what we've already talked about. One way. And we're going to be focusing on flow. Local autoregulation here. We are focusing on blood flow. It does affect pressure a little bit. So remember, we're talking about regulation of blood pressure and flow, both. This first one, autoregulation, is more so a regulator for flow. It indirectly affects pressure, of course, but it's more so about flow. This is what we've already talked about. Local autoregulation. What we're talking about is how our arterioles constrict and dilate. If we need more blood flow to an area, what do? Dilate. If we need more blood flow to an area, more flow needed, we dilate. What if less flow, blood flow, is needed? We constrict. This is what I was talking about with exercise. You already know this. I'm going to write it down. It's going to look fancy, but it's really not. What new color can I use? Blue. At rest, we're going to vasodilate. We're going to vasodilate our arterioles to where? Muscles. When we are exercising, we enlarge, we vasodilate the arterioles to muscles because we need more blood flow there. At the same time, we vasoconstrict to where? Our gut and our kidneys, because we don't need as much flow there. That is it. We can locally regulate, local to the muscle that's working. If I'm doing legs, I'm going to vasodilate the arterioles to those leg muscles. If I'm doing arms, I'm going to vasodilate to those arm muscles. So we already know this, the principle that we can constrict and dilate those arterioles to alter blood flow. This is the number 1 way that we can regulate flow. We do it all the time. Now, I'm going to talk about the other 2 when we meet in person next, but I'm going to move ahead, and I'm sorry that, I'm sorry that I'm going through these so quickly, because there's a slide later that just shows the amount of blood flow that we're able to do this. Here we go. This is showing what I just said. Look, at rest, couch potato dude, versus exercise. Let me do the exercise example first. During exercise, we're going to increase flow to the working muscles. This shows soccer players, right? They always choose the weirdest, dumbest pictures, but as a class, we could take them on. Haha. When we are exercising, we vasodilate to where the flow is needed. Look at the diameter. They're showing you vasodilation. At the same time, we vasoconstrict to our intestines and kidneys. They're showing you here a little bit less blood flow. The opposite is true when we're at rest. When we're at rest, that's when we vasodilate to our intestines. That's when our body can afford to send more blood flow to our gut to digest the food. Where, if we're at rest, we don't need as much blood flow to our legs because they're not exercising, so we vasoconstrict. It is a big difference. You don't have to know these percentages, but I wanted to show you to what extent we can do this. So we have our same examples when we're at rest and when we're exercising. I want you to see to what extent. When we're exercising, look, 71% of my blood to muscles. When I'm exercising, what goes to my digestive tract? 3% to my gut. That is huge. What is it like at rest? At rest, 27% to my GI tract. And only 20% to muscles. So your muscles have the biggest change. Your muscles are thirsty, working cells, and we've got to feed them. We've got to fuel them. So we can send, look, 50% more blood flow to those working muscles. That's insane. Where's that 50% more blood flow going to come from? Well, some comes away from the gut. Some comes away from the kidneys. Isn't that wild? You don't need to know those numbers. You need to know this. During exercise, where are our arterioles dilated? Where are they constricted? At rest, where are our arterioles dilated? Where are they constricted? You need to know that. But I just wanted you to see to what extent. If I finish this, we talked about the equation, putting together the equation as it relates to resistance. That was our garden hose example. And then lastly, we introduced regulation of blood pressure and flow, and we did number 1, which was local auto regulation. Our ability to vasoconstrict and vasodilate as a way to alter blood flow. And you need to be able to know during exercise versus rest. All right, this is your charge until I see you next time. When I see you next time, we will delve more into regulation and flow. You're going to want to make sure you have this down because we're going to be talking about the renin-angiotensin mechanism. So much fun. All right, see ya next time, folks.